In this video, we're going to be covering different types of data and how to enter it into SPSS. First, we will be looking at the different types of data that you can record, operations that you can have with each type of data, as they can differ based on the level of data, and different and optimal ways of plotting each type to accurately represent the type of information that you have. And finally, we'll be putting all of these together and adding them to SPSS. As scientists and researchers, especially, we need to understand our data to be able to use it effectively and, more importantly, correctly. Software like SPSS only do what you tell them to do, not what you actually want them to do. So if you don't understand the data, you run into issues where the results that you're getting are not accurate and not representative of the information you actually want. So just remember the motto from programming: garbage in, garbage out. This is what we're trying to avoid. We're using the optimal ways of interpreting information in order to make the optimal analysis choice. There are two main groups of data. There is categorical data and numerical data. Categorical data can be further subdivided into nominal and ordinal data. Nominal data refers to any type of data that does not have a particular scale and is normally grouped into categories. So nominal comes from name, so any type of data that is normally labeled or has particular names, such as different colors, different days of the week, or different fruit, would be nominal data. So imagine if you asked individuals what type of fruit they had for lunch, the answers they would give you cannot be put on a particular scale. They can only be taken as if they said apple or orange or grapes. You can just put them on a list, but you can't rank them in a specific way. There are no distances between them. They just are whatever the answer was. By contrast, ordinal data does have some sort of ranking. So if you would ask individuals what they thought of a particular movie, they might say, I really liked it, I didn't like it, or I'm somewhere in between. Because of that, you can have ranking between individuals on how they considered a particular movie. Even though the distances between said rankings is impossible to tell, you can still say somebody said they really liked it while this other person said they didn't like it. There's clearly a difference there. For nominal data, there's a special category called binary data. So this refers to anything that only has two categories, such as flipping a coin where you only have heads or tails, or if you label things in terms of a successful event or a failed event, things of that nature are called binary data. But this can easily refer to anything that you decide to only put into two particular categories. The second form of data, numerical data, can be further split into discrete data and continuous data. So discrete data simply refers to any data that cannot take intermediate values. So for example, if you count people, you can only count them as wholes. You cannot have half a person. Similarly, this might refer to events that are themselves quantifiable, such as how many accidents happened in a particular city, what was the answer to a particular die toss, how many people are living in a particular building. While continuous data refers to numbers on a particular range that can have any value. So for example, height or weight, any of these can have any value in between 0 and technically infinite. For continuous data, this can also be split into two categories. There is interval data and then there is ratio data. These are important as the type of tests you run differ based on the type of data that you have. So interval data normally refers to continuous data that does not have an absolute 0. So for example, you can think of temperature in Celsius, where 0 degrees does not mean the absence of any sort of temperature. It is just the 0 point on that particular scale, as it refers to the temperature of water. However, it's completely valid to have negative numbers. So because of that, while the differences between 10 degrees and 20 degrees and minus 10 degrees and minus 20 degrees is the same, so you can quantify it, you cannot have ratios between them. You cannot split or divide particular temperatures and say this is twice as hot or twice as cold as something else. For the type of tests and data you will have, you can think about this in terms of answers to a particular question or answers on a test. So you can measure people saying you got a first, so you got something like a 70 or 72, and somebody else got a 35 or a 40. And while you can measure and say one is larger than the other and how many points difference is there between one and the other one, you cannot say in terms of absolute values of people's knowledge. So you cannot say that somebody that got a 35 on an exam is half as knowledgeable as somebody that got a 70. However, you can make such claims with ratio data. So this might refer to things such as a person's height, a person's age, a person's income, where they have a fixed zero. So if somebody has age 0, it means that they are at the start of their life. There is nothing below age 0. So because of that, you can actually quantify ratios between the data. You can say that somebody's twice as old as somebody else, and you can have intermediate values. Speaking more formally about this type of data, we can say that categorical data is qualitative type of data, while numerical data is quantitative type of data. Considering nominal and ordinal, we say that nominal data refers to unordered categories of data belonging to which is mutually exclusive. So for example, somebody can be a smoker or a non-smoker, or they can have blonde hair or brown hair, but they cannot belong to multiple categories at the same time. This is very evident when you look at binary data, where you can either have yes or no answers, true and false, and ones and zeros. For ordinal data, this is ordered categories of information. Again, these are mutually exclusive, so people might rate something as low or high or moderate, but only one of them at a time. So belonging to one of them means you cannot belong to another type of category. However, the values themselves are not equidistant. That means that the difference between a 1 and a 2 might not be the same as the difference between a 2 and a 3. So we can't make those types of claims. This is typical of, let's say, Likert type responses, where you have a scale from 1 to 5, but you can't say if the differences between each individual point is the same as between two other points. When considering numerical data, we say that discrete data refers to whole numbers, things that can be counted, tallied, or quantified in terms of physical events, and the values themselves are equidistant. So we can say that a tally of 5 is half as big as a tally of 10. While for continuous data, this refers to uh, any data that can take a value within a particular range. So for example, length, where you can have any range between 0 and infinite, they can take any point in between those. So you could have 1 centimeter, 1.4 centimeters, 100, a kilometer, it doesn't really matter. Now, the distinction is a bit tricky between interval and ratio data. The best way you can kind of remember it is that you cannot have ratios when you're looking at specific interval data. So the best you can do is addition and subtraction, or multiplication and division are only saved for ratio type data. So ratio data is the one that has a fixed and definitive 0 point, which allows you to have division and multiplication and just have ratios of different data points. So this table overviews the type of transformations and operations that you can actually do on each type of data. You can probably come back to this later on when you have collected data and want to know exactly what you can do and can't do with it. For example, with nominal data, the best you can do is provide frequencies, make statements that one category might be equal to another one, but you can't say things like, is one actually greater than the other one in terms of values, and the best you can present is the mode for the data that you have. While for something like ratio data, you can do all of the possible operations, allowing for a lot more flexibility in terms of the tests you can run and the way you can represent the data. This is why this is considered the best form of data to try to collect if it is actually possible. But if you can't, you need to know what is actually feasible to do with the data and what would be incorrect. So for example, if you had ordinal data, but you would be reporting means and standard deviations, this would be wrong. I know that some researchers might actually do this, but most of the times they are mistaken and you cannot make these types of claims. Due to the differences in the type of data, it also means that the way you represent it, at least graphically, matters, because there are some correct ways and some incorrect ways. Here I kind of suggest some of the best ways for you guys to report them. So for example, if you have nominal data, it's best to just represent them as a bar chart with a count of each of the different categories. The same goes with ordinal data. This can be either in count, frequency, or as percentages, while binary data is typically represented as something like a stacked bar chart, which is reflects the two type of percentages of, let's say, yes and no, which add up to 100, so it's easy to interpret in terms of how the distribution might differ. While for numerical type of data, discrete is normally represented as bar charts. Again, this is also good for grouping, while continuous data is normally represented as a histogram, so you give the viewer an idea about what the distribution of data actually looks like. Does it follow normal distribution? Does it have a different type of distribution? Relationships, so for example, between two variables is normally represented on a scatter plot with a potential trend line in between to show individuals what the trend in the data indicates, while differences between groups is normally done using a clustered bar chart. So this is typically what you see in published papers where they're comparing two types of groups on two different things like treatment and a control group on different forms of psychotherapy to see what the outcome might actually be. Again, it will be best to come back to these after you have collected data and want to know how best to represent it to make sure that you are accurately communicating information to your readers. Now, you may be thinking to yourselves, this is a lot of information about data. Why do I need to remember all the different types of operations for different type of data, which I can use and which I can't use? Well, it's because the analyses, the tests, and even the graphs that you are creating rest on particular assumptions. If your data doesn't actually meet these assumptions, you can't do the test. Technically, you can do the tests, but the answers you will get are wrong. This is a big problem with tools such as SPSS, where you can click different things and output is going to appear, but the information in that output is going to be wrong if you didn't know what you were actually doing. Consider this analogy. Your car is a machine that runs on a specific type of fuel, let's say diesel. However, technically, you can put any liquid into the tank, including paint. The car doesn't know what type of fuel it needs, nor does it need to know. You do. If you put the wrong type of fuel, your car will stop working. However, when it comes to SPSS, it will rarely tell you that what you did is wrong, so that's why you need to know in advance that what you're doing is the correct way. We're going to be looking at this in a bit more detail in the third video when we're looking at inferential statistics, but I'm going to be briefly going over some of the examples of how your data should look like and what you can and can't do with it. Now I'm going to briefly go over some fleshed out examples for each type of data. You don't need to remember any of the stuff that is on these slides. It's mostly so you have an idea how each type of data should be represented and analyzed. You will be able to come back to these later so you can tell that the analyses you are conducting on your own data make sense and are following the correct standards. So let's say we want to collect some nominal data. We might ask individuals what course they are studying at Kingston. So just a simple question where they can say different things, or they might have a list and they just tick which one represents their course. Let's say we collected 10 answers. So what can we do with this data? Well, the best you can do is tally it or maybe turn it into a percentage. Then after you've done this, you can represent these graphically either as bar charts or pie charts, depending on which one you think looks better and is easier to read. Now, you might want to know if in your particular sample, the distribution of courses mentioned follows a particular uniform distribution, so meaning that all of them by chance should be about 25% because it's a fourth. But maybe it doesn't. So in this case, looking at the graph, you might say, well, it's clear that criminology outweighs the other one, but you can't actually make that statement unless you're conducting some inferential statistics. So in this case, you would conduct the chi-square goodness of fit test, which on the data that I created shows that there is indeed a statistically significant difference between a distribution that follows chance, meaning that all of these should be flat and equal, and what we are getting at the moment. Now, in more advanced lessons, you could actually look at which one of these are higher than chance and which ones are less than chance, but for now, this is what you would typically be reporting. You'd be reporting the value of your inferential test, the p-value in terms of how surprising is the data, a confidence interval for the estimate that you've done, and an effect size to show how strong the effect actually is. For ordinal data, a typical research question might be asking people the strength of their preference for something. So for example, how much do they like their Netflix subscription? You might give them options ranging from extremely dislike to extremely liking their subscription. Let's say you collected 100 answers with this particular question. Again, you could be looking at percentages, so you have an idea within your distribution how these values range. You might then decide to represent these graphically using a bar chart. So these shows percentages on each of these distributions, with indifferent being in the middle. Now, the question you would normally ask with ordinal data is that you have an expectation that people should be neutral. On any scale you give them, people should technically be neutral. So to test if their preference for Netflix deviates from this neutral midpoint, you would conduct something like a Wilcoxon-Sines rank test to determine if this does follow a different type of distribution. In this case, based on the data I've created, it does show that there is a significant difference, meaning that the ratings are not equal to the midpoint value, in this case being indifferent, and they are skewed in a particular direction. To be able to say in which direction, you normally report something like the median or the mode, but not the mean. So the median or the mode to show to your readers which one is more favored. So in this case, it will be moderately dislike. For interval data, a typical question might be, let's say you administered Beck's depression inventory to 300 people. So this is a psychometric tool aimed at assessing depression. It has 21 items and a range of 0 to 63 points. Again, this is interval data because the 0 point is not an absolute value. This means that if somebody scores a 0, does not mean that they have 0 depression or 0 mood problems. To say if somebody scores 63 does not mean that they have absolute depression. And more importantly, you cannot make ratio judgments such as saying that somebody that scores a 20 is half as depressed as somebody that scores a 40. The way you would normally look at this type of data is you might calculate a mean and standard deviation for the sample. So in this case, the mean rating is about 19. The way you would represent this is typically with a histogram to show the population distribution for these particular scores. And you can see kind of where the mean is and how it kind of deviates, with more extreme scores being very rare. The way you would analyze this to see, does this follow a typical normal distribution, but more importantly, does the mean of the sample differ from a specific value that you might think is relevant? So for instance, with the BDI, 16 is typically the cutoff criteria for depression. So you might care if in your sample, the mean is different from 16, meaning is the sample more likely to have higher depression scores than, let's say, the typical population. So the way you do this is by looking at the one sample's t-test, which for the fictitious data that I created shows that there is an indeed statistically significant difference and a pretty large effect size, indicating that my sample has a higher depression score than would be typical for a population. Finally, with respect to ratio data, this is what you would typically see in experimental studies when they are published. You might have a research question such as differences in reaction time after drinking coffee as compared to simply drinking water. So this is ratio data because reaction time can range from 0 to infinite. So it does have an absolute 0, but no actual endpoint. So let's say you collected 300 individuals, half of them were in group 1 where they drank coffee and half of them were in group 2 where they drank water. What you would first do in terms of descriptive statistics was just calculate the sample mean and standard deviation for each group. So in this case, the reaction time for water was on average 400, while for coffee it was 250. You would typically represent these using clustered bar charts. So in this case, you have a bar for water and one for coffee, with the standard error being represented. On this axis, you have the actual reaction time. Now, if you want to tell if there's an actual difference, although in this case it's pretty clear that there is one, but you can't really make that judgment without having some inferential statistics. So the best way to do this for this type of data would be with an independent samples t-test. And my fictitious data, this revealed that there is indeed a statistically significant difference between the two groups. The effect size between them is pretty astronomical, but that's because of the way I created the data. And this is typically what you would report to mention to your audience alongside the descriptive statistics in terms of the difference between the two conditions. Now that you have an overview of the different types of data, we'll be looking at how you input each type into SPSS. So now we'll be looking at SPSS. When you first open it up, it will be presented with this window, which allows you to either type in new data or open an existing file. In your case, you'll be typing in the new data, but for this particular example, I've created some data in advance. So here I have a data file that I created that has all the different types of data that you might want to introduce into SPSS. One of the primary things you'll notice is that in terms of measurements, SPSS only cares about nominal, ordinal, and scale. So it basically puts together the discrete, the interval, and the ratio data together because the operations that it does doesn't really care about which subtype it is. But for our understanding, it does matter, especially in terms of how we report the results and how we ask questions. So for instance, let's say I had a study where I collected data from 20 individuals, and I collected different types of data. So in terms of nominal data, in this case, I just looked at the degree of study. So this has, in my case, 3 categories. The way this is represented in SPSS is, if you look here on the nominal variable, I have a label to remind myself what the question actually was. This is also useful as it comes up in the output that SPSS provides. And then I gave my data some values. So for example, in my data, 1 is coded as psychology, 2 is criminology, and 3 sociology. So for instance, you can edit these any way you want. You can change the labels that you give them. It doesn't have to be 1, 2, and 3. You can also add a 4th one, and this is where you would do all of this. Moving along the column, you select nominal data for this type so that SPSS knows what it is that you are actually doing. So you can flip through the 2 types of viewing it, so you can either see it in the way that it is coded or the labels that you actually assigned to each of these variables. This is relevant as sometimes you might open a file and it looks like this and you have no idea if these are actual numbers that you need to do something with. So are they counts or are they frequencies? And then you can check to see if they actually have any labels attached to them. So in this case, as I mentioned, nominal data does not have any sort of ranking order. The way this little icon is displayed, it just shows that there are different categories that can be put in any sort of order that you would want. However, when it comes to ordinal data, this is not the case. So in my particular example, I created a scale that looked at feelings about the course that people were on, the options that I gave them. So if you go over here on the ordinal data, it says feelings about the course, and I gave them 3 options. So it could be 1, I hate it, 2, I'm kind of meh, and 3, I love it. Moving along, you see that I have labeled this as ordinal data, so SPSS knows what this actually is, because otherwise it doesn't know. So if I move it to say something like nominal, it doesn't know that this is incorrect, so it will analyze it as nominal, the same as if I put it as scale. So in this case, I have each individual person's rating of the course on my specific measure. So if I would want to look at how my sample performs and what their ratings are, I would look at the ordinal value, and this would basically have the scale that I'm interested in from the most negative to the most positive. Moving over to scaled interval data, as you see, these three at the top have the same type of icon. There is no way to distinguish between them. The distinction has to be made by you. So even if you look at the variable view, there is literally nothing here that can distinguish them amongst each other. The best you can do is decide if particular values can have decimal places. For example, in terms of interval data, as I mentioned, it may take on a specific intermediary values, but most of the times it's going to be whole numbers. The same with discrete data. So in this case, I modified the decimal points to be 0, meaning that the values, when they are represented, should have no decimal places. If I edit this, it will appear, even though they make no sense. So 2 decimal places just appeared, but they mean nothing because you cannot have intermediate values. But this is important because the databases that you will be using might not always be your own. So you might be getting a file from somebody else, let's say for the exam that you have, so you have no way of knowing what these might be unless you were part of the collection process. So this is why it's always important to label things properly, assign them the correct values, and make sure that they are on the correct measurement scale. For continuous scale values, you basically, in this case, I had them as glucose level. So in my fictitious experiment, I wanted to see if people's performance on a particular test, so in this case was exam marks, affected how much their blood sugar level changed throughout the course of the exam. So I wanted to see if people that, let's say, did not like a particular course, when it came time for them to actually take the exam, if their marks had any sort of impact on their glucose level, and let's say the final outcome. A third variable that relates to discrete data, because this again is a type of numerical continuous data, not continuous, sorry, discrete. I looked at the number of pages that they used in their exam. So this again shows that you cannot have half a page. In my case, you only had full pages that were being counted, so you can see for each individual on their exam how many pages that they actually used. So each type of these data can be analyzed in different ways. They tell us different things about the sample, but what is important to remember is that the way you code them, the way you describe them does matter, because these values mean nothing. So 1 here is not the same as 1 here or 1 here, but if you look at it like this, they all look the same, and SPSS would have no idea what the differences are. You would need to know. A few more elements that I think are relevant is that you can also input other types of data into SPSS and have it remembered. For example, you can have a data. So the date that something happened, you can tell SPSS that you are inputting a specific date. So you can select here the type of data that you actually want, and SPSS will understand this is a date. It doesn't change. It's not something that you want to actually analyze, although technically you can analyze these types as well. You can also have participant codes, or in this case fictitious names, that you would input as strings, so people know that these are characters. You could have these as questions or something along those lines to have in your data. And I always put an index category, so in case SPSS decides to flip these around or move them in some crazy way, I always remember the order in which I introduced my data. Again, this has no value, it's only for me, so I actually remember what is going on. So this should basically cover how most of this type of data is recorded and how it is represented in a database, so you have an idea about what your file should look like and what you're aiming to code your variables in based on what your research question is.